So my name's Stuart Haszeldine. I'm chairing today's session on behalf of the UK CCS Research Centre. I'm a geologist at the University of Edinburgh, and in the UK CCS Research Centre, I'm one of the leads on looking at CO2 storage. And the theme we've put together today is to have look at 3 different engineered test sites around the world, because a lot of effort, time and skill goes into designing and running these test sites, and they're unique opportunities to gain high quality measured information about the behavior of CO2 in the underground. And so what I propose to do is run through the 3 sites without much of a break between them. We'll maybe have 1 or 2 questions only after each presentation, and then we'll have a much longer general discussion of about 40 minutes at the end. So I'm hoping we'll run through, and after about 20 minutes after 3 o'clock British time, in an hour and 20 minutes, then we'll have a general discussion from then onwards. So there's the presentation running order. So the first presentation will be given by Dr Stuart Gilfillan, who's also from the University of Edinburgh, senior lecturer in geochemistry, originally a geologist, but did his PhD on noble gases as tracers for natural CO2 accumulations, and since then has built up a whole set of expertise in tracing CO2 in natural sites, in engineered sites, and in industrial processes, and even in the deadly oil and gas sector to try and differentiate different reservoirs. And so using these noble gases and other isotope systems as tracers is gives very good insights. So Stuart's going to talk to us about looking at the FRS test site, which is in Alberta, in the plains of Alberta, in a very simple layer cake geology system. So we'll see how simple or not simple that is. Over to Stuart.
Okay, thank you very much, Stuart. So I'll just share slides, which hopefully has brought me up to the title slide. Hopefully you can all see that. And I'll just sort out my pointer so I can see. Can somebody just confirm that I've got a laser pointer there for you to see?
Yes, you have.
Yeah, thanks, Gareth. Okay, so slightly different title, just because this is sort of what the work is based on, which is looking at the geochemical baseline for CO2 monitoring at the Carbon Management Canada FRS station. And just like to start off by thanking the 2 co-authors who've done the bulk of this work, which is Rachel for her PhD studies at Edinburgh, and also Emma, who's a postdoc here working with me on this, and also a Canadian, Nick, who's been invaluable for collecting some of the samples during COVID, and Kirk, who's also a sort of walking encyclopedia of the knowledge of the site. And without further ado, talk on to what we're actually trying to do. So part of all of this session is about how we can learn from test sites into regular deployment of CCS technology. And some of these test sites, or this test site in particular, is interested in understanding the potential migration pathways of CO2. Obviously, we're always interested in the means to determine the fate of injected CO2, both in the short and the longer term. And knowledge of geochemical baseline conditions prior to injection and how these can change post-injection is also pretty important in terms of understanding what we can do and how we can determine what's going on in the subsurface. And that rolls into really part of this, or the main key part of this work that I've been working on for a number of years now, which is looking at the effectiveness of inherent tracers. So moving away from what I think is fairly unrealistic ideas of doping CO2 just because of the volumes required for large scale storage, but actually looking at the tracers that are inherent to the CO2 you inject and how they can be used. And really all of this is all about developing and testing the methods to verify secure CO2 storage for regulation, for carbon credits, for monitoring, and for obviously site handover and things like that. So moving on to the FRS site, where is it? So just to put down here at the bottom, this is Canada. So we're in Alberta in Canada, in a town called Brooks, famous for being one of the largest meat processing plants in Canada, apparently, which you can definitely tell when you visit the place. And it is just out to the outskirts of this on old land that has been donated by a hydrocarbon company and is actually in a producing active area. So there's actually a gas field well that we also sampled here. This is the FRS site itself, consisting of an injection well, several observation wells, so geochemical and geophysical, and water wells to assess things around the site stratigraphy. This is what it looks like if you happen to have a drone flying around. So this is just showing you the injection well. They've got a CO2 tank. They've got buried geophones, various things involved with the injection of CO2. And then you can see this, they've also got various different geophysical techniques embedded and put into the site. In terms of where they're putting the CO2, so they're injecting it into this Upper Cretaceous basal belly river fluvial sandstone formation with a foremost formation seal of mudstones and an injection zone around about just below 300 meters depth. So fairly shallow. It's all aimed at resolving and working with gas phase fluids. There's lots of other things going on. I'm only going to talk about one particular bit. This is just to show what we've got. Not going to go through all of this, but there's continuous monitoring, both in terms of things related to injection. There's geophysical monitoring related to all the things going on periodically. And then there's also geochemistry involving various different aspects. And I'm really going to talk about some of the groundwater sampling from wells, fluid sampling and analysis, and then these tracer studies, but there is a whole compartment of other things going on. And just to say, there's quite a few other people involved in the site. So these are just some of the joint industry partners that the site has had invest in it. So moving on to today, what I'm going to talk about is the work that we've been done effectively characterizing the baseline of the site prior to CO2 injection. And this is just showing you the geology's injection zone about 295 meters into the basal belly river sandstone. And then we've got various sampling points highlighted here in red in terms of from the deep injection formation via the geochemical observation well. We've also have surface casing vents, which basically sample from the casing or the bottom of the casing. And then we have a couple of water wells that are also instrumented with sampling ports. So the West Bay multi-level sampling well, and then also just a typical domestic water well as you would get on a farm, just to show that. And then last but not least, we also collected samples from beneath the site at the Countess gas field. So what we are really aiming to do with all of this is to fingerprint the gases that we found in and around the site, both CO2 and methane. And whilst these may look to the untrained eye like just molecules, they've actually got inherent isotopic fingerprints, which are very useful for us tagging or at least resolving the origin and tracing injection of CO2. The other thing that's associated with both of these, both in the natural environment and in the injected CO2, is trace components of the noble gases. And they are excellent tracers of things happening to these fluids or these gases. So what we're really aiming to do here is look at the methane on the site, because we know the areas are producing active site for methane production, and fingerprint that to identify its origin, and then look to see what the injected CO2 in terms of what's in that fingerprint and how we can use it to track the migration and fate. So moving on to fingerprinting the methane. Putting this really simply, we look at here the ratio of the light hydrocarbons, so methane gas itself relative to heavier hydrocarbons, ethane and propane. And that gives a diagnostic range distinguishing between those methane that's produced by bugs versus methane that's produced by the thermogenic cracking of a hydrocarbon-rich or kerogen source rock. And what you can see here, these are the two ranges in here. In red are the bulk of the sample data. Unsurprisingly, the one we got from the deeper gas field underneath the site is thermogenic, very clearly thermogenic in origin. The vast majority of the other samples are close to the biogenic range, but importantly not quite. And then we do have a slight sniff or a trend, and particularly in one of these samples from early on in the sampling, to indicate that there was thermogenic gas contribution to that particular well. And that's indicating that all of these have got some component of thermogenic gas in them. They're not solely biogenic. We can then look at this related to plotting up the carbon isotopes here in the methane against the deuterium isotopes, obviously methane being made of hydrogen and carbon. And again, we can then fingerprint this origin a bit more clearly, looking at exactly which bugs are producing it. So in this case, fermentation of acetate is where the vast majority of these samples plot. But again, we have evidence of a slight sniff coming down, or a trend, particularly in this sample, going down towards the thermogenic methane, and thermogenic methane again in that deep gas field. And then we also have some potential influence from bugs that are producing methane from CO2 reduction. However, this trend actually going off in this direction can also be explained by actually simply oxidizing the methane, or some oxidation of that methane. So that doesn't necessarily say that we've got actually a separate source of the biogenic gases. It's probably more likely that this is just reflecting oxidation of the methane. Moving on to noble gases, so just a little bit of background on this. So noble gases in crustal fluids, something I've spent quite a long time looking at, and they are very useful for tracing different things because they have different sources. We're not going to talk about the mantle side of things because we don't have any influence of that, but we're mainly looking at atmospheric components, and clearly in this case, or what we definitely have in this case, is a component from the radiogenic. And that's from radioactive decay of natural uranium, thorium, and potassium in the Earth's crust, the subsurface, that generates these particular isotopes of noble gases. And we can use those for dating how long the gas has been there, for instance, and also identifying inputs of deeper gases to shallow levels coming from the Earth's crust. So looking at this in terms of the noble gases, we're plotting up here the helium ratio, so the helium-3 to helium-4 ratio. So this is looking effectively at the component of deep sourced radiogenic helium-4 relative to what we have in the atmosphere, this value up here. So this is a ratio actually relative to the level in the atmosphere, because there's actually very little helium-3 present in any part of here. Helium is very useful because it gets lost to space. So technically, whenever you have the helium making its way to the surface, it tends to escape off. So we don't have a huge amount of it. So it's a really good way of tracking for the input of deeper fluids or deeper gases in the subsurface. And what we found is all of the samples very clearly. So looking, this is the ratio we have in air of 1. And all of the ratios we have in all of the samples, both the waters and the gases, are considerably lower, below half what we have in the air ratio. And as we get down here, we have considerably more helium-4 input, which is way above what we would expect to see in a shallow groundwater in contact with the atmosphere. And what this is telling us is all of these samples have got more helium-4 in them than you would expect if they were just from contact from aquifer recharge. And then also what we can see is as we move down towards the hydrocarbon field and some of the into the injection formation, we find increasing helium-4 input. We also pick that up, as I say, in the waters, and we can actually plot just a mixing line between the atmosphere and the this deep gas sample that we have from the wells underneath, or the field underneath, and come up with this. And this ratio just down here on the x-axis, sorry, to show the helium to neon ratio, which again is effectively a test of how much helium-4 we have, and that's how we can generate this mixing line. So we wanted to know where this helium is coming from. So particularly looking at the groundwaters, you can actually model how much helium you would expect to generate using the uranium and thorium concentration of the rocks. And this is what is plotted here. And these lines, these are just showing with depth as the uranium thorium content would increase and you have less diffusive loss of helium, then you would expect to follow this trend. And what we find in this domestic water well in particular is that the helium-4 values are higher than you could produce in situ in the host rock stratigraphy. So therefore you've got to have an excess of helium-4 from some sort of external source. One other thing worth pointing out, which I'll quickly point out, is that you also see quite a bit of variability in some of the samples, even from the same sampling points in the same wells. It's particularly the case for the surface casing vents, which are these things popping up off the side of the well. And these are typically in Canada left open just to vent the casing gases to the atmosphere to prevent pressure buildup. And what we found is actually quite a bit of variability from sampling these, probably related to different shut-in times prior to sampling and possibly atmospheric pressure variations as well. So that's something that was useful to find out. And moving on to the last little section in terms of monitoring the CO2 at the site, we also measured the noble gas fingerprint in the CO2 that's being injected. You can see that here. Well, up, so this is the sample relative to the concentration or the ratio, sorry, in air. So this is the 20-36 ratio. It's tied into argon 36. So there's a tie point here, 84-36 ratio, and the 132 xenon to 36 ratio. You don't need to worry too much about this. Just effectively say this is effectively a genetic fingerprint of the gases that are in the site, and then this is a genetic fingerprint of the CO2 that's being injected. And you can see that CO2 is distinctly different to what we have in the injection zone. And that has good implications for monitoring. It's quite positive outcome for the monitoring of things. So we can plot up, again, a mixing, again, just showing this 84 krypton 36 ratio against the krypton concentration here. And we can plot in what's in the baseline good reservoir sample versus what's being injected. And we can see that actually it's quite sensitive for detecting even a very small amount of CO2, which may be difficult to pick up. You can track this ratio, and that's particularly the case for the xenon to argon ratio, which is also highly sensitive, provided it's just simple gas mixing. And that can be used as a tool to look for the sort of arrival of, or the early arrival of the CO2. We can also look at this for monitoring overburden. So this is plotting up a very similar plot. This is the mixing within the injection formation, again here. And then we've also plotted up here, mixing with the most air contaminated sample, just to show that actually it's still reasonably sensitive, but not quite as sensitive when you're actually looking at migration through the overburden. Should be said, this is assuming just gas phase migration without significant diffusion or advection or changing of the noble gas fingerprint, which is subject to further modeling work that we're undertaking. But it does show you that it's less sensitive for the krypton to argon ratios, but for the xenon to argon ratios, we still would be able to pick up a reasonable chunk. And that basically means that should there be a difference in CO2 concentrations related to shallow processes such as soil gas and plant respiration, we could look for this xenon to argon fingerprint to actually determine between that natural CO2 increase versus the CO2 increase caused by migration of the injected CO2. So just to sum it up, just about in time, we've got stable isotopes of the methane showing a predominantly biogenic source, but with some evidence of contribution from a thermogenic source as well. Noble gases highlight a consistent and clear excess of radiogenic derived helium, and these helium values, excess helium is observed in all of the groundwaters, especially in the domestic water well, and we can't explain that just by in situ generation, so there has to be an external contribution of helium-4, and these helium values in these water wells can also be attributed to potentially be attributed to that well being completed in coal seams. And we know from previous work that we've done, coal seems to be quite an effective trap for helium in certain places around the world. So what's probably happening is that coal is acting as a trap of the crustal flux of helium potentially. And last but not least, we can say we need to underline, be careful about how we sample, particularly from casing vents, and that the noble gases, particularly krypton and xenon ratios relative to argon, can provide monitoring tools for the future of the FRS and potentially other sites. And I will leave it there.
That's great. Rampant applause all around. Thank you very much, Stuart.
You're welcome.
So we're slightly over time, but if anybody has a burning question, a single question they want to ask, then please ask that now, and I'll see if, I don't know if I can actually see the questions or not. Chat, yeah. Okay, so if you've got a question into the chat, and I don't see any questions in the chat at the moment, so that's fine. As I mentioned at the start, then we'll come back to all this and be able to have a more general discussion about what you can determine from the deep underground with these different isotope and geochemical systems and geophysical systems. There'll be a chance to ask questions later. But what I was struck by was that even in a very simple layered sedimentary rock system, then you can deduce quite a lot of complexity, that it's connected to a lot larger volumes of gas than you might first realize. It's absolutely not just as simple as drilling into biogenic methane, which is locally derived. Great, okay.
Yeah, thanks.
Thank you very much. So I'm hoping, is Max Watson, has Max arrived? No? No, okay. Jakob, are you perhaps ready to go next if there's a hiatus in our plan running order?
You can try at least.
Yeah, okay, thank you. So I'll just introduce you and Auli, and then if you two go as a pair, of course, like you planned, and then we'll put, if Max manages to arrive, we'll put him in at the end of the sequence. Is that okay with you? Yeah, fine, okay. So we were going to talk about Otway, the Australian Victoria Australian test site, but Max has not arrived because it's the middle of the night in Australia. So, but I'm very pleased to introduce a double act now to talk to us about the Helix test site in Israel. And that's a pairing of Jakob Bensabat, who I can see on my screen now, who's Chief Technology Officer and owner of the Environmental and Water Resources Engineering company in Haifa, Israel. And Jakob's done lots of work around Israel for government work and for commercial work. And really, I think probably identified a potential site on a buried structure, 1,500 meters depth or so, which was then Auli and Jakob got together a team of scientists, international scientists, and have basically run 3 large European funded projects on this, understanding the site, developing the site, and then finally managing to do a test on that. So Jakob will go first. He's, again, as the doctorate in civil engineering and founded the company, I guess, in 1992. And then Auli will follow on afterwards. And Auli Niemi is a professor of groundwater modeling at Uppsala Earth Sciences Department in Sweden, where she leads a geohydrology research group. And Auli has an impeccable set of academic credentials with a PhD, first of all, at Helsinki, then spending time at several labs in the United States at Princeton, MIT, Lawrence Berkeley National Lab, and then coming back with multiple jobs in Finland and rising to full professor and now Dean of Earth Sciences in Uppsala. So it's a good pairing of practical application and academic insight, hopefully. So over to Jakob, first of all, and we'll see if you can get through the slide pack. Over to you.
I'm trying to figure out how to share that file. Do you see it?
Yep,
perfect.
Great.
And you're off.
So I have 12 minutes to tell about a lot of things. So first of all, together with Auli, we managed to have a number of projects on the CO2 storage and based around the Helix site in Israel. And I will talk about a little bit about the objectives of the experiments that we carried out at the site, and then a little bit about the resources that we were put inside in order to carry out these experiments. So the first one was probably the site selection and then the site characterization and the site preparation and doing all the risk assessment and what is called HSE, which means health, safety, and environment, that goes with all the facilities around above the ground. And then the definition of the experiments that we wanted to carry out and the protocols that determine the flow work for the experiments. So the objectives of the experiments were for us at least to understand processes that are more complex and less investigated, generating data sets for validation, and testing of technologies of monitoring that are most commonly used in CO2 storage. And we had another objective like the impact of chemical composition of the CO2 stream, which we were ready, but then the project gets finished, and while all the preparations were made, we did not manage to do the experiments themselves. So the objectives of the Helix experiment included the quantification of the trapping mechanism that Auli will explain probably later on, the impact of the heterogeneity, and having a kind of comprehensive data sets that could be used for modeling later on. For that, we had 2 wells that were drilled, one at the depth of, both at the depth of 1,650 meters approximately, and with a layer called the Helix sand layers of the lower Cretaceous. We could have more layers to open, but we wanted to have the maximum impact possible for a limited amount of CO2 to be injected. So we limited ourselves to a very small layer of a thickness of about 9 meters. The wells were designed to be able, one for injection and one for monitoring. And both wells we had monitoring technologies, as well as a capability to abstract water from the wells via via airlift, and also doing fluid sampling in both wells, pressure temperature measurement, and DTS. So the reservoir is relatively optimal for CO2 storage, large depth, sufficient pressure and temperature, adequate location with regards to safety, not very close to an urban center, but not far away. So all the logistics were relatively easy to put together. The site is a depleted oil field, so we know a little bit about it. There were about 60 deep wells drilled over an area of 10 square kilometers. So the geology was well defined, and the hydraulic properties, at least from the wells that were drilled, were quite okay, as well as the hydraulic conductivity from 100 millidarcies to 2,000 millidarcies, and porosity between 15 to 25%. So this is the Helix site with all the wells that were drilled, and our site was at Helix 18, somewhere here. So this is a structural map of the top Helix sands, and as you can see, it's a very small structure with very high impact to result of injection. The yellow lines are the K, W, and A layers, which constitute the Helix sands in which the injection of CO2 was supposed to be made. So this is the structure of the well, the design of the wells. It's a typical oil well structure with a cap rock, a low, a kind of dolomite layer, which we didn't perforate through in order not to have to deal with fractured rock. And then we have the 3 sand layers separated by clay layers in between. So this is an aerial photography of the Helix site with the 2 wells in them, and the land that was allocated for the whole site. So the characterization that we did was essentially first to do a hydraulic test, because the hydraulic properties of the area, to my point of view, are the key element to determine. So we conducted a pumping test. We bought a specific pump, and we conducted the pumping test so to be able to determine the hydraulic permeability, the hydraulic conductivity of the well, of the formation. And we found that it was quite okay, of the order of about 500 and 700 millidarcies. So this is the pump test and the interpretation of the pump test. We also had cores that were analyzed by a number of teams in Edinburgh and in Göttingen and in France, in Montpellier at CNRS, if I don't miss anybody else. There was also seismic monitoring conducted by Vibrometric from Finland to get a baseline, and also after a little bit of CO2 injection. And the well's structure included pressure and temperature measurement at 2 different horizons, which proved to be a very wise decision that we didn't make on purpose, but was very useful. DTS for continuous measurement of temperature, and also fluid sampling system, a U-tube divine from class 6 from Barry Freifeld. And altogether, that was for the injection well. The monitoring well had almost the same setting, at the exception that, of course, we couldn't inject CO2 through it. CO2 injection was limited to the injection well. We cemented the well with a dedicated cement purchased from Halliburton, and inside there was a tube, an injection tube, and layers of safety, packers that sealed what we call the injection chamber from the remainder of the well. So if something went wrong, we could seal the packer and just close, isolate the area where the injection takes place. This is a more realistic view of the completion, but and how things went through the packer. So the site layout included, beyond the 2 wells, well 1, well 2, 18A, 18B, the area of the control room, gas storage, CO2 heater, CO2 injection kit, and here the wellhead. So this is a view of the control room, which had all the monitoring lines converged to the control room. That included the tube-in-tube of the sampling system, the DTS, and basic lab facilities inside, like a mass spectrometer, pH analysis, etc. And also gas detectors for CO2, for H2S, and in order to be on the safe side, and that was required by the authorities in Israel. So I don't want to get into the details, time is running, but we had, this is a picture of the tube-in-tube. It looks complex. We also had the ability to measure the pH of the samples, the downhole samples, with a device that was developed together with CNRS and was added to the U-tube system. And we had an injection kit that included a heater based on gas fired together with a low flow pump and a high flow pump. The system included the CO2 gas tank, a booster pump to increase the pressure, and 2 pumps, a low flow and high flow. High flow pump to inject pure CO2, and low flow pump to mix the CO2 at a certain depth to the water in order to obtain saturated CO2, or just to mimic the injection of trapped CO2 in the formation. So from an operational point of view, it is very important, and this for those who want to do CO2 injection, to be on that side of the equation of state of the CO2, not depressurizing too much the system, because then we start to having hydrates and solids, and then we clog all the system. So that is one of the really things that we need to worry about. The initiation of the injection is I think of interest. First of all, we saturated all the well with gaseous CO2, so we had gaseous CO2 at a pressure of about 20 bar, and then we started to increase the pressure and then inject supercritical CO2. So this is the pathway to the injection on a time base. Also, when we wanted to inject water, we had to have a control of the water that is injected. And also, in order to avoid the well clogging, what we did is we did an electrolysis of the water to be injected, which was saline, in order to create a high concentration of chlorine, which is a very good product for avoiding generation of organic matter. So we also had a tracer injection system through a chemical line that was connected at the depth of 1,000 meters. This is the PNID of the system. It was quite complex. We could inject krypton, xenon, and SFX, and we actually, I think, did all three. And we were able also to, well, I will skip that. So this is a picture of the first experiment that we carried out with the team from EWRE and Uppsala University. You can see Auli here monitoring the flow, and me trying to control the wellhead. So that is the logistic ways, the CO2 tank, and finally self-release of the well after the injection of CO2 as part of the experiment. So I think that I will leave to Auli here, and thank you.
If Auli, yeah, full screen, thank you.
Can you see my screen now?
Perfect, yes, that's
Yeah.
excellent.
So thank you very much for giving us the possibility to talk about our work. And I try now to give a very short summary of two of the main experiments that were done at Helix, residual trapping experiments. And I want to acknowledge some of the closest co-workers who have recently been analyzing the data here at Uppsala, and then of course Jacques Bensabat. And there is a long list of co-workers which is listed here that are co-authors in the papers that we have been publishing on the data. So I guess you will get this slide so you can see these names. So the objective, I will first say a few words about how to determine residual saturation in situ. And then I will explain in an outline way the experiments that we did at Helix. And then look a little bit at how we interpreted the results and what we found out in terms of the residual saturation, and also a related concept that came up in our results, the critical saturation, and then some conclusions and implications. And of course, I understand that everybody in the audience is familiar with this plot with the residual saturation as one of the trapping mechanisms in CO2 storage. And this lower panel here tries to show that we are trying to make this kind of a residually trapped zone in our deep reservoir formation. Here is a presentation or a sketch how to determine residual saturation in, let me see now, sorry, I was wanted to get rid of something here that is disturbing my own view. This is actually originally proposed and implemented at Australia Otway, and I was thinking that we will have an Otway presentation before us, but it will go like this also. So the concept is that you do characterization tests, hydraulic test, tracer test, thermal test, before you have any CO2 in the system. Then you create a residually trapped zone in your formation. And then you repeat such tests, hydraulic, thermal, and tracer tests, when you have the residually trapped CO2 in your formation. And the difference tells you about the spreading or how much CO2 there is. And so the hydraulic properties change, the thermal properties change, and tracers, you use this kind of gas partitioning tracers that go into the gas phase. So comparing these two gives you an idea of how much CO2 you have in your system. Then generating this residually trapped zone, this plot shows here now you first inject CO2 in your deep reservoir, and then you somehow get rid of the mobile CO2. And you have two basic ways. Either you withdraw the mobile CO2 by pumping, or you inject water that is saturated with CO2 and push the mobile CO2 away. And then you have your residually trapped zone, and ideally, and can repeat your tests. And as I said, this was first proposed and done at Otway, and I guess we will hear about their experiences. And we have then proceeded with and added our own things. And I want to point out this special collection of papers in the International Journal of Greenhouse Gas Control that came out, was finalized last year. So it summarizes the most of the interpretation work so far. I'm having trouble moving on my slides. I don't know. So, okay, Jacques already showed a lot of pictures from the site. I just want to emphasize that there was a very thorough site characterization work going on. So we actually made a special edition also in International Journal of Greenhouse Gas Control 2006, explaining the site characterization and the equipment and so on. Then to the actual residual trapping experiments. So 2016 was the first experiments, and there the main characterization test was hydraulic and thermal tests before and after creating the residually trapped zone. And then the zone of residually trapped CO2 was created by first injecting CO2 and then withdrawing fluids until the residual state was achieved. And first, actually, the mobile CO2 was allowed to self-release and then were pumping. And there were two methods in looking at when are we at the residual state. Because this is not straightforward when you are pumping CO2 from your system, that when are you at the residual states. So we used indicator tracer, but that turned out to be not so. It was theoretically good, but actually in practice it didn't help us. But then simply following the pressure profile, we had these two pressure sensors in the test interval, and we were kind of looking at how the difference in those sensors, it told us if there is just water or if there is CO2 coming into the well. Then the second experiment, 2017, then we also had a partitioning tracer krypton as a characterization method. And in this experiment, the zone of residual saturation was created by first injecting CO2 and then pushing the mobile CO2 away with CO2 saturated water. So these were two different approaches. And this is now the time sequence of the first experiment with all the dates. And this part here that is circled, that's related to creating the residually trapped zone, CO2 injection. Then there was a heating experiment, but that's another thing. And then opening the well and letting the CO2 release in a geyser-like manner, and then pumping. And here we deemed that now we are at the residual states, so we stopped the pumping. And it is these tests that are my main characterization tests, a pumping test, and that were done before and after to see how much CO2 there was in the system. And this is actually showed this picture already from the field. This gives some of the key data that was collected from these pressure sensors, pressure and temperature in these two sensors at our layers. These are the two reservoir layers. And we see the CO2 injection, water and tracer injection, CO2 injection. Here the well was opened and it was self-releasing in a kind of geyser-like manner, pumping, and these are the actual hydraulic tests before and after, and temperature effects, of course. So now this data was then used for modeling, and we modeled the full sequence of this with a tough model, and a key parameter was, of course, this relative permeability functions that were determined in the laboratory by the Stanford group, and it is this parameter here, this residual gas saturation, that we were kind of then looking that are we getting similar value in the field and in the laboratory. So we were varying the permeability, porosity, and these characteristic functions, etc., within the range of the measured data. And like said, we had very good data constraints actually already from the site characterization program. And we could see that these are the data fitting pressure, temperature, and flow rates, what we could measure. And we could see that varying the the pressure signal came very good signal of the residual saturation. You can see here that if this parameter residual saturation is 0.1 or 0.2, we get a big difference. So this was a very strong and robust signal. The temperature data also gave us information about how the CO2 was distributed there. It went primarily to the upper layer and less into the lower layer. So the conclusions from this first experiment was that the hydraulic test gave a strong signal and good estimate of the overall residual gas saturation. Temperature data provided additional information about the gas distribution between the two layers, as did the two pressure sensors, how there was a difference between them. And the model analysis suggested that most of the gas tended to enter the upper layer, which is not so surprising. And we get an estimate for this maximum residual gas saturation, which is the value in these functions, 0.1, which is lower than what was determined in the course at the laboratory, which was 0.2. Then we moved on next year to this second experiment. We call it residual trapping experiment 2. And here we had the tracer also, and in addition, a different way of doing this residually trapped zone. So now this part is the where you see the circled, where the residually trapped zone is done. Here is CO2 injection. There was some other experiment, some heating experiment going on here also. Then the same thing, that opening to create the residually trapped zone. So the well was opened, there was a self-release first, and then these blue pillars here are where water with CO2, saturated with CO2 was injected into the system, and this was done in intervals because there were some technical problems. This is far from straightforward to do this water saturated with CO2 injection. And then these were now the referent test, heating tests, and then the partitioning tracer test, first injecting the tracer and then withdrawing, same here. And this is how it looked in the field. Here the partitioning tracer injection is going on, and here is sampling. Now the U-tube or tube-in-tube sampling became very important when we had the tracer. Again, these are the pressure and temperature data. I'm not going to go into the details, but they are meaningful, varying in a meaningful way, of course. And again, we use this to fit our model, and especially the pressure data and tracer data in this case. And then these are the tracer, this partitioning tracer krypton breakthrough curves recovering. So this tracer test was this kind of push-pull experiment, of course. So the first tracer test, which was done without any CO2 in the system. So that was, it was very easy to fit with the previously fitted model from the previous trapping experiment. So this told us that we didn't essentially do any, I don't know how much, we didn't do any model calibration actually. The data and the model fitted very well. So this tells us that we had a good understanding of the site as such. But then when the CO2 was in the system, in this residual, presumably a residually trapped zone state, so then we get this delayed peak that our models whatever we did not really capture. So with residual system, CO2 in the system, the delayed peak was very difficult to match. And we carried out an extensive set of simulations by varying everything we could think of, formation parameters, partitioning coefficients. We even did this kind of stochastic models, stochastic heterogeneous models. We had some quite good idea how the heterogeneity on the site could be. But even then our models came to this part while we had this delayed peak in the real data. Finally, we could match this. We could, again, the most of the CO2 entered the upper reservoir, and water and tracer tended to enter the lower reservoir. There was channeling type of behavior, but then also we had to do an artificial blocking of the flow for the first 5 hours. That was the only way we could explain this delayed peak. And this was, of course, not very satisfactory to us that our models didn't have a physical process that would explain this. So then we started revisiting a concept called critical saturation, which is well known in oil and gas industry. Maybe many of you are working with that kind of applications also, but it's not really addressed, at least not in the field scale in the CCS. So if you think that you have a pore space here now, and the red dots is your trapped CO2, and you have water there, and the white is the rock. When you have a system that is at the residual state, gas residual state, then when gas starts to enter the system, or there will be more gas, in our case, because of exsolution and gas expansion, because we were pumping the well, so we caused the pressure decline, and that in turn causes exsolution and gas expansion. So when you have that kind of a system and you have your saturation, gas saturation increasing, the system does not become mobile right away, but it needs to be connected. And this is the phenomenon of critical saturation. So here we have the classical gas relative permeability curve, where first gas is entering the system, then water is entering, and we get into this residual gas saturation. And then when gas starts to increase, gas content starts to increase due to this exsolution and gas expansion, I'm sorry, my pointer. So the relative permeability does not become non-zero immediately, but the gas content has to increase quite a bit to this critical saturation. And we denote the difference with this term here, SG mob. And even then, after we have reached this critical saturation, it's slower, this increase in this gas relative permeability. And yeah, this just shows that the slope even beyond this critical saturation is less than in these previous curves. And this did not exist at least not in TAF2, and probably not in the other major CCS simulators at least. So we implemented this process and took values that are meaningful from the gas and oil applications. There are no data on CCS. And to our great joy, this could actually explain our delayed peak. So with meaningful values for this difference term 0.05, we could get a very nice match. And then giving what kind of value we give to this difference, it determines the location of our peak. Now, we were, of course, very happy that with the physically based processes, we could explain this observation in our data. The slope of this curve did not influence in our case too much. Now, how am I doing with time? I came now to the conclusions, but should I rush through them?
No, you just carry on talking, Auli, because that's very clear. It's good.
Yeah. Okay, so then implications and conclusions, general first. So first of all, we have presented procedures and interpretations for determining residual gas saturation in situ. As far as we know, there are not, other than Otway has been really doing this kind of dedicated experiments. So we hope they are of interest to people. And the value that we got for the residual gas saturation was similar from the two experiments, but less than the laboratory value. So it was 0.1 versus 0.2. Then in terms of determining residual saturation of the methods, so our conclusion was that hydraulic test gave a very clear signal concerning the overall, what we could say, effective residual saturation of the interval. Thermal test gave additional supporting information, as did this monitoring the pressure profile in the injection well. So it was very good to have two pressure pressure sensors there. Partitioning tracer was much more complicated to carry out at this kind of depths. It was very delicate equipment. We actually had to replace the sampling equipment, I think twice, or replace once and repair. And also it's more complicated to interpret, but it in principle gives more detailed information about the channeling and the gas distribution in there. Then in terms of creating the residually trapped zone, again, in just a kind of a subjective view after working with this. So the fluid withdrawal, it is quite simple and robust approach to do, and good if it's combined with this pressure profile monitoring in the borehole, which gives an impression of whether the gas is, whether we are pumping gas into the well or water saturated with gas. Injection of water saturated with CO2 is again technically challenging. It's difficult to optimally mix the CO2 and water in this very deep borehole, and it's easily, you have an oversaturated system where there might be gas blocking, or you are under saturated conditions, and then you are dissolving your residual water. Of course, our models can handle this kind of things, but I would, if one was to do these kind of things in a simple way, the fluid withdrawal was quite good. So then this critical saturation, this is of course a kind of an observation that took place in this case. So when we were lowering the pressure, we caused gas exsolution and expansion, and we needed this introducing this, we could say, relatively new concept of critical saturation. Like said, it's well studied in oil and gas industry, but not really considered in CCS. Sally Benson's group has done some laboratory experiments where they have observed this kind of thing, but in the field I haven't seen. So it needs to be accounted when modeling scenarios where there is unexpected pressure decrease due to leakage or something, and that then can lead to gas solution expansion. I need to point out that when you are injecting CO2, when you are increasing quickly the gas saturation, then this should not be so important. This is a safety enhancing process because it delays the gas mobilization. So with this, I want to thank you and all these EU projects and also some funding from the Swedish sources. And we, as I mentioned, there is an earlier special edition of the site characterization. And then now we have this special edition or special section of articles about these interpretations of this, about these trapping experiments. And there are two more articles, but there are the articles that I was citing. And then this critical saturation, it says here accepted with revision, but it's in press now. So this is all information. So yeah, with this, I want to thank you and of course, take your questions. I'm sorry if I went over time.
No, that's ideal, Auli. Thank you very much indeed. And a huge amount of information, but also coming to quite understandable but powerful conclusions, I think, from that, with some very new information. So Max has joined the call now, I think, from Otway, but I'll just pause for a minute in case anybody's got a rapid question to ask for Auli or for Jakob. And I don't see any new questions in the chat. So you've got a few seconds to put something in if you want. Otherwise, we'll come back to the questions which have already been asked.
We actually see Stuart's hand there. Is he? Does he have
a hand? Right. Okay. I can't see any hands on my screen.
Yeah, I'll just go just really quickly.
Yep,
so Ali, thanks very much for a really interesting talk. Just wondered, was there a reason, an operational reason, why there wasn't any tracer sampling within the first, I think, fifth, whatever it was, within that first peak? Was that?
Yeah, there were sampling problems, so it was technical difficulties.
Okay, thanks.
Yeah, I mean, I got the impression the whole project is very not simple, so that's why the pairing together of Jakob and Auli is, I think produced a great result. Okay, I think that's Stuart's legacy hand still, is it?
Yeah, I'll put that down.
Right. Okay, so again, we can come back to a more general discussion, I hope, as we proceed, but we should have Max online now. Is Max there? Yep, I see you on the
Stuart,
call.
I'm here. Yep.
That's great. Happy afternoon in the UK then, Max.
Yeah, apologies for being late there. I just don't know why my alarm didn't go off.
Psychology,
hopefully,
right?
Yeah.
Anyway, I'll just introduce you and then you can go ahead. You've got your, whatever it was, 20 minutes or so, and then we'll have a general discussion after that, assuming people have stayed. And so, as was alluded to in Auli's talk, then there's a huge, hugely impressive test site called Otway in southern Australia, and that's been running for about 15 years, I think, something like that. And Max Watson here is the Senior Manager for Technology Development from CO2 CRC, and has spent a long time, 20 years or more, in petroleum and carbon capture and storage, and a lot of that working on this test site to plan, execute, and actually implement the large-scale subsurface experiments, at really full-scale, unique experiments in the world. And as I think you'll see from his slides, then what we're looking at here is something like maybe 3 or 5 years to plan and develop the hardware for the experiment, and maybe a year to drill a hole or two, and then just a year to actually make the measurements. So it's really lots of planning and a quick burst of activity, leading again to some pretty interesting results. Over to you then, Max.
Thanks, Stuart. Let me share my screen. Okay, can everyone see my screen? All
Yep,
right.
if you put that on full screen,
Yep.
that's it, perfect.
Fantastic. Okay, well, thank you very much for inviting me, Stuart, to present at this. I can talk for days and days about all things Otway, but this one's very much focused on what we call Otway Stage 3 experiment. Now, this has, as you said, Stuart, been planned for many years, and we've only just recently undertaken the actual injection operation for that. So the results you'll see through this are the initial results, and we're working through those results now, and we'll have some more detailed conclusions over the coming months to years even. Before I commence, all these Otway projects, they take a lot of money. Working in the subsurface is a very expensive operation. So want to acknowledge the financial support from ANLEC, which is supported by the Low Emission Technology Australia. Also want to acknowledge the Australian government and our specific technical support that we get from our Stage 3 partners. So Curtin University, CSIRO, Lawrence Berkeley, and many others, and many commercial partners as well. Just for those who aren't familiar with CO2 CRC, so we're a research organization, member-based research organization. We've probably put in about $150 million in research, very much focused on the maturation of technologies from a lab scale and sort of initial research fundamentals through that field phase, and really assessing that valley of death that technology can fall into from time to time before it gets to that commercial readiness level. So we work very closely with our industry partners and our various research institutions to find ways to bring their technologies to the field to trial as technologies. And you'll see with the Otway, we're very proud of it. It's one of the most comprehensive field facilities in the world to really trial and develop these different technologies, and that can revolve around storage. We do also do some work in capture, and we're moving into different areas, which I'll go into. Now, just as a bit of a history and context for the Otway project. So the Otway started in 2004. And basically, the initiator for the project wasn't an idea around a suitable technology to trial or anything like that. It was really finding CO2 that we could use for a range of different experiments. And we found a natural CO2 occurrence at a well called Buttress 1, which was a CO2-rich gas field that was discovered in the very late 1990s, which was about 80% CO2, the rest being methane. And we found that next to a range of different depleted natural gas fields. So we purchased one of those as well as that CO2 field to allow us to do these different experiments. So from 2004 to 2009, we looked at a depleted reservoir storage demonstration. So this was down, you can see my mouse here, at about 2 kilometers depth, where we really just showed the concept of CCS by injection into this depleted reservoir and monitoring that migration up dip towards a pre-existing production well. We got a little bit more sophisticated then from 2009 to 2019, and we heard mention of a few of the experiments we did in what we call Otway Stage 2. But this was looking at a depleted, sorry, not a depleted reservoir, a deep saline formation instead, about 1.5 kilometers depth. And we went through a series of different stages in this experiment, looking at how to best characterize saline formation, including looking at a lot of different techniques to test and characterize the residual or gap trapped volume of CO2 down there through huff and puff type techniques. And then after that, we did a 15,000 ton injection operation to show the distribution and growth of CO2 through a sophisticated seismic monitoring approach, and also then show that stabilization process through that as well. And that was recently concluded. Stage 3, which is what I'm going to talk about today, that evolved to something where we had a offshore storage partner who really needed a solution different to surface-based seismic acquisition for monitoring their CO2 plume. So we developed ideas around different monitoring techniques that could overcome their challenges in surface-based monitoring, which had a low impact and which they could get the information that they needed on demand and also targeted towards the key areas of risk. So I'll go into the details of that throughout this presentation. Looking forward, we have been developing a shallow CO2 controlled release migration to look at the role of faults in controlling CO2 fluid flow in the near surface. We are in development of an Otway Stage 4 experiment. We've been working quite closely with a consortium of research groups called GeoSequest, and we're hoping to do a trial of their advanced modeling systems by undertaking an injection and monitoring operation. And we'll probably link that up with other optimizing storage techniques and trial those as well through that process. And then a little bit further down the line, we've just started pre-feasibility trials. Pre-feasibility work on this is the idea of doing an underground hydrogen storage demonstration, again down here in the depleted reservoir. But that's going to be progressing slowly. We're still in the very early pre-feasibility days, but if that does go ahead, we'd be looking to do a series of injection and withdrawal cycling operations down there as well. So the Otway, we've done quite a bit of work, and we do feel that the system works exceptionally well for trialing different technologies. And Otway Stage 3 was all about innovative monitoring technologies to really help address some of the challenges in finding fit for purpose data, being able to get monitoring data that's on demand. So you can almost press a button from the office and get the information you need about your system. And we've managed to bring that down to getting that information within a couple of days. We want that to be as cost effective as possible. And when we first proposed downhole monitoring solutions as an alternative surface-based systems, a lot of people laughed and said, well, that's going to be ridiculously expensive. We have done techno-economic modeling of that, and we've found cost decreases of 50 to 75% using these downhole monitoring systems. So it's an amazing cost saving as well. And it does that with a very minimal impact to the environment, to local operations that are occurring, and to the community as well. But very generally, what we looked to do was an injection, another 15,000 tons of CO2, and use that volume of CO2 in the subsurface as a basis to trial these different monitoring techniques. And that includes downhole permanent seismic monitoring systems, and pressure tomography and inversion as well. So this is an aerial shot of our lovely stage 3, our Otway system. For those not familiar with Australia, we're in Victoria, and the Otway International Test Centre is along the southern coast in Western Victoria. I certainly encourage anyone who's able to come to Australia to come to the site. We're very close to Port Campbell and the 12 Apostles, which is one of Australia's famous natural landmarks. We try very hard to keep the operational footprint at our site as minimal as possible. And this is probably one of the busier times at our site where we're drilling the injector well for the stage 3 project. This is normally dairy country, and we've got cows wandering across this system quite happily through much of the years. As well as the operational area for our CO2 storage trials. If we follow to the north, and I always forget where this is, just over here is our plant for our CO2 production, and there's about a 3 or 4 kilometer long pipeline that connects that CO2 source to operations to the south. Doing any project in the subsurface does take quite a lot of pre-planning and effort to make sure that we understand exactly what the scientific objectives are, and how we'll have our chances of success in achieving that. To get the approvals in place to do this operation, to ensure that we do it safely. So you can see, this project was conceptualized back in 2017, and we have worked through this to the execute phase where we started drilling our wells in 2019, the monitoring wells. We did drill an appraisal well, which turned out to be the injection well earlier than that. And then we started our injection operations in around December 2020. All sorts of challenges with that associated with COVID and travel restrictions and lovely things like that. But I'll get into the details of that as well. Now, the injection operation was to see CO2 flowing from CRC3 up dip in this direction to the east. And we wanted to place monitoring wells that wouldn't encounter the CO2 directly, but could observe from a distance. So we did the drilling of those monitoring wells, 4, 5, 6, and 7, as directional wells from 2 drilling pads, again, to minimize the impact on the surface. So I'll go into the details of what we put down those wells. Generally, each well was targeting a depth of a bit over 1.5 kilometers. CRC3, we put tubers and packers in, while CRC4, 5, 6, and 7, we kept those fairly simple and didn't need to put any tubing into those wells. The injection well, we cemented the latest and greatest in fiber optic technology for DAS and distributed temperature sensing as well outside of the casing. And we had to go through a fairly sophisticated process to make sure when we perforated that well that we perforated in an orientated direction away from those optics, fiber optic cables. As well as that, to compare the difference in performance of the fiber outside and inside casing, we also clamped another fiber to the tubing. Also positioned fiber pressure and temperature gauges at the reservoir interval, and also monitored wellhead conditions as well. For the monitoring wells, we followed a similar technique. We put the engineered fibers outside of the casing, We didn't follow with another one inside because we'd already demonstrated the difference in performance with fiber inside and outside of casing. And we hung the pressure temperature gauges at the reservoir depth in this case, just to simplify the wells to what we needed to do. Now the stage 3 injection operation that commenced around the 2nd of December 2020. Again, we were using our buttress gas for this, and we injected at about 140 tonne per day. And we broke that injection operation up into 3 intervals, where between each interval of about 5,000 tonnes or so, to undertake some what we call sort of baseline seismic acquisitions, also to do the pressure tomography operations at the start. But then we also started to look at doing pressure tomography whilst injection was occurring to compare those differences. So because we're using new technologies and trialing the performance of those new technologies, we certainly wanted to make sure that that we had a benchmark to compare to. So we did do more traditional seismic surveys. So we took a baseline and then at a couple of key intervals throughout that operation. And as well as that, we did our more innovative pressure and seismic monitoring activities as well. I won't take you through this one. It's fairly straightforward. So it shows when we did the injection, when we paused for our first surface seismic acquisition. These numbers M6, 7, etc. They're monitoring surveys, and we've done a lot through the years, and this is the 7th seismic survey that we've done, but the first for the stage 3 project. And progressed through that process, and now we're in this phase of data processing and analysis. Now the buttress plant, that's mothballed for a lot of times, and it gets turned on fairly intermittently when we want to do an injection operation, and there can be a few little teething problems when we turn the system on, but it did pretty well. There was some initial startup operational issues, but after about 3 weeks, and you can see in the diagram here the ups and downs a little bit of the pressure profile from buttress and into our monitoring system, the CRC 3, 4, 5, 6, and 7 wells. And aside then from a few power supply issues that we suffered from, the plant actually performed pretty well. Now we used Curtin University in particular for the seismic elements of this project, and then including acquiring that initial survey to baseline our site. So we did that early in 2020, but that was when COVID really started to settle in Australia. Not that we had many cases, but it did cause us to have a lot of travel restrictions from in between each state, and also within the state as well. And the Curtin University group, who are based out in Perth and Western Australia, were not able to stay in Victoria, so they were demobilised. I think because when we designed the Otway Stage 3 project, we designed it to be an on-demand monitoring system. We're actually pretty good with the setup of telemetry, etc., to be able to operate this site. And very fortunately, we're able to find locals, and the Otway is within a petroleum region of Australia. So those locals knew how to operate the seismic vibrosize equipment. Very fortunately, so in connection with the University of Curtin and those local crew, we were able to conduct the monitoring surveys quite effectively. So this is just showing the fold that we're getting around those wells with that 3D VSP survey that we did. So we're using vibrosize, and you can see the lines where the vibrosize trucks ran across the different surveys, and then you can see around each well and the performance of those fiber optics to give us reasonable fold for that seismic operation. Now, pressure monitoring was one of the key technologies that we really wanted to trial this in this operation. So there was two technologies that we're looking at in particular that I'll quickly cover today. So that's pressure tomography and pressure inversion. We did look at earth tides as well. So each monitoring well was equipped with the necessary downhole pressure gauges, and we're also set up to be able to inject water to create pressure pulses from those monitoring wells to try to create an image of where that CO2 is progressing through your reservoir. So the way pressure tomography essentially works is, you're creating a pulse of pressure from each of your monitoring wells by water injection, and that pulse of pressure that will attenuate as it reaches and crosses through the CO2 plume, CO2 being a more compressible gas than water. And through some pretty sophisticated algorithms, you can then find the edges of your CO2 plume. And from that, you're creating basically a rough map of where that CO2 is in the subsurface. Now, this is an early image, and it's showing from CRC3 where the CO2 plume is roughly, and a pre-existing plume that we did in the stage 2 operation. So this was captured after about 10,000 tons of CO2 being injected, so February last year, and we're building on this work, but it's performing quite well to give a rough representation of where that CO2 plume is using this pressure-based approach. So that's looking at CO2 in the reservoir itself. Another technique we wanted to trial was a bit of a what-if scenario. What if, in a commercial sense, there was a leak of CO2? Would you be able to triangulate where that is using pressure inversion techniques? And we use the injection as a quasi for a leakage event. So we knew very well where the leak event was occurring, and we were able to test the approach of pressure inversion techniques to try to triangulate where that event is occurring, and that performed pretty well too. Now, for downhole seismic, because we wanted an on-demand system and we wanted a low-impact system, what we were looking at was the performance of stationary orbital vibrators to create the seismic source, and pairing that with the downhole fiber system and DAS for distributed acoustic sensing for detecting that seismic signal. So we placed quite a few of these stationary orbital vibrator systems around our site, and we worked quite closely with Lawrence Berkeley and Curtin University to develop those. And we ran these stationary orbital vibrators almost on a daily basis. And what that essentially did was create multiple transects through that injection area, that monitoring area, to see how that plume evolved through time. This map's just showing the different transects that were created with the placement of our stationary orbital vibrators and our monitoring wells. And it was configured so that we could get a new image of that plume every couple of days. So that commenced with the onset of the CO2 injection. After about 300 tons were injected, we were able to detect, using this system, the presence of CO2. This is just showing, relative to the baseline, that development of that plume, and you can see with the arrows where it is after a week, month, or 3 months of injection. This is from CRC4. I'm not sure why they chose this well as the best well to show, because CRC4 was probably the most challenging of the wells that we used. And this is just showing the difference map of that plume as it evolved. So conclusions to date, and we're certainly still working on the finalization of the review of the data that's come from this project. But it's looking like the stage 3 techniques are meeting the requirements that were established, low impact, low cost on-demand monitoring quite well. We were able to test that, in anger with the onset of COVID and the travel restrictions associated with that, and really were able to run quite a sophisticated operation, from our offices for the majority of people involved with that, and fairly minimized on-site support, which was fantastic. The results we're seeing so far, they're looking like they both are performing quite well in plume detection. Particularly we've seen with the maturation of technologies around fiber and the stationary orbital vibrators, that they perform incredibly well in quite high resolution monitoring of that plume. We'll certainly be continuing to analyze and mature those technologies over the next months to years to see how we now move that to a point where it's commercially ready as different monitoring techniques. So that was a very quick run through of the project. Got to acknowledge all our members and research partners and sponsors associated with the project and CO2 CRC generally. So thank you very much for your time, and happy to take any questions.
That's great, Max. Thank you very much indeed. Really clear, and both an explanation of the amount of preparation that needs to go in and the difficulty of actually getting real measurements. But I'm glad you survived the COVID test, which was inadvertently dropped upon you.